we will come to the last speaker and the first speaker. So it's my pleasure to announce again Paolo Franchin as the final speaker. And he will conclude the webinar with the presentation on integral abutment and cable stayed bridges. So please, Paolo, the floor is yours again.
Thank you, Christoph. So integral abutment, cable stayed, and next to those bridges. So these are clauses 9 and 10. Clause 9 on cable stayed and next to those bridges is very short, 2 pages. I will deal with it at the very end, and I will focus on the more substantial clause on integral abutment bridges. So first of all, the scope. Clause 10 should be used. Let me see if I can. Yes, here, sorry. Is the pointer. Applies to integral abutment bridges, but it's also permitted its use for the semi-integral abutment bridges. Semi-integral are bridges like this, for example, but in reference to the presentation, my colleague David, these are all those bridges where an abutment is connected with the deck and exchanges forces, so that deck vibration engages the backfill or natural soil behind the abutment. So not just this example, but there's alternative examples. So there's a very large number of configuration for integral abutment bridges. Some are shown at the beginning of this clause. What is important to keep in mind is that whatever is the configuration, the specificity of these bridges is that soil structure interaction is something that, unlike other bridges where you can sometimes model them as fixed base, here must be considered is a distinctive feature of these bridges. So the global dynamic equilibrium of these bridges, the vibration cannot happen independently of the surrounding medium, unless the clause says specific provisions are taken to avoid or minimize interaction. So when we say something like this, what we mean is solutions that have been also tested in a shake table test, and they are explored, of, for instance, having compressible inclusions right behind the abutment wall. So in these cases, of course, the interaction with the backfill is limited, and the method that I presented in clause 10 need to be modified. So just 3 slides on the practice of EAEE construction in Europe, just to show that there are different positions. These are like solutions that are common in Italy. Composite deck, usually composite decks are used, and they can be single or multiple span decks with both full height abutment on single row piles or bank pad on single row piles. These are both used. Composite decks with integral abutment are common also in Germany. Single span with straight or even inclined abutments. And I should have mentioned that in the 3-span case in Italy, where I'm speaking from, it is common to have the deck sliding over the intermediate piers, but there are also cases like the Slovenian practice, at least I'm aware of, where the deck is in concrete and the piers frame are monolithic with the deck. So this clause needs to cover for all these cases. So let's go to the basis of design. Since interaction with the soil is an essential part of the response of these bridges, like it usually happens when you have to deal with soil that is not is more difficult to characterize than artificial material, it is wise to use upper and lower bounds soil properties. So you need to analyze everything with 2 sets of soil properties, because, for instance, considering like a lower mechanical properties for the soil will increase the loads carried by the piers, especially when they are monolithic. Actually, when they are monolithic with the deck, and higher mechanical properties will increase the internal stresses on the abutments. So you need to consider two. This is a should, a recommendation. Then there is a permission to include in the calculation of the response the effects on the soil pressure of the construction sequence. This is important. This is true in general for all large structures, but in this case, even if they are not large, for these bridges, the construction sequence influences the internal forces at the end of the construction, and this may lead to different initial state of pressure behind the abutments, and thus influence the starting point for the dynamic analysis. This is mainly something that you can do when you perform displacement-based analysis, the displacement-based approach, and perform a nonlinear analysis. In the simplified force-based approach, you cannot consider this. You will see why. Also, there is a permission to incorporate effect of thermal cycling. Actually, now we are dealing with the seismic design situation for this type of bridges, but most of the research, initial research on these bridges, dealt exactly with this problem, the fact that these bridges are in contact with the soil at the abutments, and through seasonal variation, winter, summer, they have a compression, elongation and contraction of the deck that brings to interaction with the abutments. And depending on the structure of the backfill, you can have in a number of cycles a considerable deformation, increase of the pressure behind the abutment, and deformation of the soil. So this is an example from work exploring this. And so depending on the type of backfill you have, you may want to include these cycles before the seismic analysis for the displacement-based approach. Now, whatever is the method, of analysis, the main feature is the interaction. So the actions should come from the kinematic compatibility between the soil and the structure. This means that there are displacement-dependent soil structures, the soil pressure that needs to be accounted for. Further, even for a symmetric bridge, the response is not symmetric because the bridge will move away from the soil on one side and against the soil, leaning against the soil on the other. So you need to consider both direction. You cannot just mirror you have to consider both direction of analysis as usual. And this is and last, and this is a very important aspect, consistently with, in general, what I was saying at the beginning, with the fact that critical zones, area where energy dissipation occurs, should be easily reachable for the purpose of accessible for the purpose of repair. Typically, especially if you have tall abutments, these bridges, the abutments of these bridges are not easily repairable, accessible for repair, unless you dismantle the entire embankment or portion of soil behind the abutment. So the target performance set by the code for these bridges, for the abutments, and therefore for the whole bridge, is a quasi-elastic response. This is a very important statement. And therefore, you have to design the parts of the structural part of the bridge for DC1. The exception to this is when, like in the Slovenian practice, you want to use energy dissipation in the plastic hinges of the piers as part of your design concept, in which case you can design these hinges, only these hinges, provided that you still have quasi-elastic response in the abutments. You can design the hinges for plastic hinging, the piers for plastic hinges to DC2 or DC3. Of course, this requires, the code doesn't say how, this requires some manipulation to do it with the force-based approach. The best approach, if you want to design a bridge such this, is to go for the displacement-based approach. Now, so two methods are presented for analysis of the action effects. One is the force-based approach, and the other is the displacement-based approach. Starting with the force-based approach, consistently with the target performance, which is DC1, one can use a Q factor of 1.5, which basically coincides with the QS, the overstrength factors. Note one important aspect of this, the design of these bridges, since the response is the result of the interaction between the bridge and the soil, and we are not using the reduced spectrum like we usually do in the force-based approach. So we are not dividing the spectral acceleration by the Q factor. We are using the full spectrum, so to find a configuration of equilibrium between the inertia of the structure and the soil pressures. And then, for the purpose of designing the structural element, we divide these internal forces by Q. In the end, for the structural members, it's the same, but the displaced shape and the pressure on the soil will be more realistic. This is just show internal consistency. The fact that for these bridges, even for DC2 and DC3, now you understand why the total Q is equal to basically to QS equal to 1.5. So how do you perform force-based approach? You have to apply total. So rather than modeling the soil in the force-based design, force-based approach, you replace the effect of the soil with earth pressures. So the problem is how to decide this earth pressure. Now, this earth pressure in the code, you don't need to superimpose the let's say static pressures coming from construction sequence. It would be difficult to determine, especially because of the phenomena we talked before, and the seismic one, like it is sometimes done for retaining structure. What you need to do is to apply a total static plus seismic earth pressure acting on the abutment. Now, these are not symmetric because the bridge moves away from the soil on one side and leans against the soil on the other side. So you have on the upstream, let's say moving away side, you very easily, because the displacement corresponding to the activation of active limit pressures are small, you go in the active limit pressures on one side, and you go to some state of passive pressure. Let's call it mobilized passive stresses, mobilized passive pressures that are intermediate between the at rest and the passive pressures on the downstream side. This is something that is already well known. It has been developed by several parties, especially with reference to the thermal expansion of summer expansion of decks for the under temperature variations. So you have active stress, active pressures you see here, at rest pressures, and you have something that is larger than at rest, let's say passive, and then going back to at rest along the height. This is things that you find in the design guide for integral abutment bridges under non-seismic design situation from the Inter project, and this is a solution for thermal for the thermal case. Now, for the thermal cycles of contraction, expansion, these are self-equilibrated stresses. So you need an iteration. The seismic case is different because you do have an external action, something that is pushing actually the structure against the soil. So in a way, it is simple. You don't need iteration. And what we do is to start from the intensity. The higher the seismicity, the higher the seismic force is pushing the deck, the structure, let's say, and the abutments towards the soil. And we normalize this intensity. Please note that the inertial forces on the structure that you need to apply are equal to the mass of the bridge times the plateau spectral acceleration S alpha. Now, this is a considerable simplification. The reason for doing this is the following. First, there are a lot of nonlinear dynamic analysis that have been carried out to support this, and this is from a parametric study with a number of bridges with different bridges of this type, number of spans. I will show more later. This is the plot of the model periods for the modes of the entire soil structure system. And while this here is the fundamental mode of this system that is more close to the deposit mode. These are the modes for, I will show their shape later, modes where the embankment and the structure are interacting more. These are the modes that really dominate, say, contribute most, we'll say dominate, contribute most to the internal stresses of the bridge. So let's call them bridge embankment modes. And it will be very difficult with a partial model like this that you have to use to design the bridge in a simplified force-based approach to compute these periods. We know that they will all be in the area of the plateau. So this is simplified. You just use S alpha as the spectral acceleration for your structure. So you have M times S alpha, and you divide it by the maximum passive stress resultant that you will have if you have developed a fully passive pressure distribution on the abutment. Now, the highest this value of alpha, the largest the proportion of the passive stresses that you will develop. The code says that then you have to use a non-iterative pressure distribution that is larger, as you see from the at rest stresses. It's passive up down to the depth delta H, and then constant. So this is the simple distribution that you have, active on the other side plus inertial forces. This is the way you carry out the analysis for this type of bridges. And it gives this expression for delta H, which is a function of the height of the abutment, this intensity parameter alpha, and C, which is a factor that regulates how much, this is based on calibration on dynamic analysis, this is how much goes to the abutment and how much goes to the foundations, of course, that are not modeled but included as impedances at the base. More on this. This is just a glimpse and a reference to explain how these profiles have been calibrated with using a full model, including soil columns and the foundation, not just the bridge, and checking what was the pressure distribution at the instance of maximum internal forces. And what you get is that as it was reported in the previous slide, you have maximum internal forces when the structure is leaning against the downstream embankment. A parametric study of a large number of cases with the single, 2-span, 3-spans, different internal lengths, different soil profiles was carried out, and the results of this linear static method with this equivalent stresses versus nonlinear dynamic analysis was carried out, and as you see, the correlation is quite good. As I said, this is the foundations need to be included, of course. Otherwise, if you cannot model this fixed base, otherwise it will not load lean against the embankment. This is one case where you also have to include the foundations, and you can do this according to part 5. Annex D in part 5 gives expressions for foundation impedances. Here, just as a way of an example, I'm showing expression for single piles, but the foundation might be shallow. As we've seen, there are different ways of building an integral abutment bridge. And of course, what is important to recall is that, if, for instance, if you have piles, then you will get forces in these impedances, the base, in the springs, and then you will have to apply these forces to an appropriate model for your piles in order to determine the internal force distribution in the piles. And this is important because it's not necessarily at the top that you develop the largest internal forces, and you may even develop internal forces that are too large in terms of required reinforcement, and you need to increase the number of piles, even if from, let's say, a geotechnical point of view, under static loads and bearing the capacity of settlements, the piles are enough. You may need to increase them for the inertial forces. What else? The transverse direction. Transverse direction, of course, it's mentioned, but it is much easier because most of this interaction occurs in the longitudinal direction of the bridge. And then, of course, you need to, but this is true in almost all cases. You have to pay attention for those cases where, so if you need to carry out the analysis in the transverse direction, you just have a deck that is restrained by abutments that can be considered rigid over their height in this respect, and consider the rotational stiffness of the group of piles. This is what is said here in this point 11. Unless, of course, your abutment is quite flexible. There are cases where integral abutment bridges are built using as an abutment a sheet pile retaining structure. Well, in this case, this assumption needs to be relaxed. You need to account also for the flexibility of the sheet piles. And of course, you can do two separate models, but in the case of skew bridges, you need to carry out a spatial to use a spatial model. Now, going to the displacement-based approach, this is treated as you see here in a very short, compact manner in the code, because most of the material is in an informative annex D. This approach is implemented either through nonlinear static analysis or response history analysis. Now, in general, you should discretize the soil domain, which is an inelastic continuum, and model it. Response history analysis should include the entire, somehow, not necessarily like this very defined model, the whole system. In the case of nonlinear static analysis, you can simplify this. In general, however, we won't go for models of this level of refinement, and the code opens to mutually independent inelastic springs. This means basically a Winkler approach. And the relevant material to implement such an approach is given in informative Annex D, which I will detail right after this. Here, I'm just mentioning, I wanted to mention this paper by Grayman and co-workers is from 1986. So in 2 years, it will be 40 years old. This inclusion of these methods that seems relatively refined was discussed a lot within the committee, and this is just to say that the application of these nonlinear Winkler models to the analysis of integral abutment bridges is by now a well-established technique. It's something that is around, has been around for now almost 40 years. So let's go to Annex D. And Annex D talks about modeling, as I said, for nonlinear analysis with the Winkler approach. Now, one important thing that is said, of course, is that you know, we are used to Winkler for foundations, and we have a constant Winkler spring under it's all at the same depth. Here we must use depth-dependent springs, horizontal depth-dependent springs, because the stiffness of the springs and the most importantly the strength of the springs depend on the confining pressure. The constitutive law should be composed at least of 4 linear branches. So these are compression-only springs, in theory, going from the active to the passive limit with 2 different stiffnesses. So the code says at least 4 linear branches, then allows to approximate it as a 3 linear spring, importantly, with the passive stiffness, because it is more important, since the maximum internal forces are when we lean against the soil and we activate the passive side to get the correct passive stiffness. So if we have to approximate, we don't want to use the active stiffness, but the passive one. And then you can even, and this is related to a question I've seen before, how do you implement this in commercial program? Unless you have a program that allows you to define springs that do not pass for the 0, point. For instance, the well-known SAP 2000 program does not allow this. All springs must pass for the 0, point. In order to do it in a commercial program like that, then you will have to correct the springs, subtracting the at-rest pressures, and apply at-rest pressures approximately with a load distribution, triangular load distribution. So this is allowed. In terms of stiffness, expression from the literature are given for the active and the passive stiffness. This K are the lower K are the stiffnesses, and then you have strength, of course, and strength. Now you see here uppercase K, which these are the coefficient, earth pressure coefficient. the strengths for these springs are not given in Annex D of Part 2. These are given as an example in Annex F from Part 5, because these are the same that are used for other earth retaining structures. And of course, the passive and active coefficients are those for the seismic design situation. That's why it is KAE or KPE. And of course, it is said that in computing the stiffnesses, these are stiffnesses secant to the expected level of deformation. So these soil modulus, soil Young modulus should be reduced with respect to the initial one, and you can use the same tables that are allowed for the reduction of the shear modulus in Part 5 to do this operation. When you do nonlinear static analysis, basically the model is the same for the structural part that we have seen before. Impedance is at the base. Linear structural model, because that's the type of performance that we expect, that we require for this type of bridges. But then we have to add springs like those that we have just described. And these springs, of course, will not be the soil side of these springs. To be more precise, should move, and it should move in order to, let's say, if you don't do this and you push against a fixed soil side, you will have a higher internal stress. So this is it will be conservative to disregard this. But in general, you can apply, you can perform even a commercial program as an analysis where you increase at the same time is a force distribution, which will be the inertial forces, and a displacement profile. The displacement profile is the deformed shape of the embankment or natural soil concurrent with the vibration of the structure. And the code gives a approximate expressions for this displacement shape. These are the modes I was talking about before. You see that the fundamental mode of the system usually is one where the entire deposit is moving and the structure is not very much deformed, and maximum internal forces occur more due to modes which involve the upper part, upper portion of the soil and the embankment. These methods have also been tested on the same parametric study in large number of cases, and of course, being nonlinear static and less approximate than the linear one, when compared with the dynamic one, perform even better. Now, nonlinear response history analysis. This is the same type of springs. In this case, there are some indications about the soil columns that one should use, and the input in this case is to be given at the base. Mostly things are done as described for response site response analysis in Part 5, and reference is made to Part 5. This is just a slide just to give you a glimpse. The fact that this type of modeling that is response here has been checked versus higher order, high fidelity complete nonlinear models. Very limited check, of course, but these show modal shapes, bending moments or displacements at the end of the construction stages, bending moments and displacements at the times of maximum moment in the piles or in the deck joint interface, and you see that there is strong support for this type of Winkler-based models. Of course, you can carry out nonlinear response analysis also on a three-dimensional model. In that case, of course, you need, and this is the necessity when the bridge is skew, and you need to, of course, not use a single layer of springs, but you need to separate these along the width of the abutment. And this is also something that is well established. And for instance, it has been shown to work very well against measurements in terms of traffic loads. So the modeling has been checked not versus higher level finite element models, but even versus experimental measurements. So just sorry for being long, just a few 3 or 4 slides on cable stay and next to those bridges. Very well known and beautiful examples. These are landmarks. Now, these type of structures are characterized by a strong dependence of the, let's say, initial stiffness matrix, of the stiffness matrix. For the dynamic analysis under the seismic action, on the stiffness matrix depends on the construction sequence. So this is just a glimpse of how one does this. This is possible to be carried out in any commercial program. You really need to follow the construction sequence to have the correct stiffness matrix at the end. So in this case, you see, before in other clauses, we saw, for instance, in the integral abutment bridges, it was a permission. You may consider the influence of the construction sequence because it's important, not that important. In this case, this is a recommendation. You should consider the influence of the construction sequence. Then we have a very strong statement. As I told you, just 2 pages, but strong statements. There is a recommendation to use response history analysis. There is an exception for multi-mode equivalent response spectrum analysis in low seismic action class. But in general, this does not seem like a very, let's say, demanding requirement, not requirement, recommendations, because as I said, these bridges are usually major bridges and they are already analyzed with higher refinement. So asking for response history is not an excessive recommendations. Of course, it is also recommended to use a 3D model and with second order effects and all this stuff. Now, another important reason for performing possibly nonlinear response history analysis is that damping is not proportional. You usually have structural damping maybe at 5% or less, but damping of cables is often much smaller. And on the other hand, you may have anti-seismic devices that can be employed, for instance, to restrain, to contain, limit the displacement of the deck with respect to the pylon, or to connect the pylon and avoid pounding. And then since you also have pylons that really load the soil with very large structure, the load transfer at the foundation in this type of bridges is very large, you have important radiation damping. So this is one case where really it is said explicitly that you should use response history analysis, possibly nonlinear response history analysis, and the model soil structure interaction, at least through foundation impedances. This is in the verification. There is actually, as with the performance requirement, it is said that also this structure should be designed to remain elastic under the design seismic action. This again may seem a very strong recommendation, but really these are usually longer period structures, so it is easier for longer period structures to remain elastic because of the lower. These are flexible structures, so large displacement but flexible structures, and usually this is the case I was mentioning. You have you use anti-seismic devices at the connection between the deck and the pylons. This is the case from Greece, the famous Rion-Antirion bridge. This is because the cable system usually provides stiffness in the longitudinal direction, in the longitudinal plane, but very low stiffness in the transverse plane, and so you need to engage the two to avoid impact with the pylon. Through them. This is just saying what I just said. I didn't remember the slide. What's going on with this? So I think I am done, and I'm sorry for taking long. I'm open to questions. I don't see you.
Okay, so thank you again for the second presentation. So I'm checking the chat. There are no questions so far. I have a short question regarding the, let's say, design philosophy. So what you showed for abutment was also the abutments with pile foundations. So I have not so much experience, but do you think that it's a good strategy, let's say, to avoid damage to piles by strengthening the backfill contribution, for example, by
strengthening? I'm sorry.
The backfill contribution, to increase the backfill contribution in order to decrease the forces in the piles.
So this is one of those
for example, through mechanical stabilization or
yes, okay. Christoph, as I have shown at the beginning, there are possible very many different configurations of integral abutments, and we should consider the whole system and of the backfill. The backfill could be stabilized through geotextiles or stabilized with the cement so we can really work, especially when because these bridges could also be embedded, no? But in the case where you have approach embankment, you can really work on the embankment material. So this is, and you have the possibility of realizing a compressible layer, a buffer between the abutment wall and the backfill. Now, this is one of those cases where, you know, the design is interesting because you have concurrent and opposite requirements coming from one action and the other. For thermal expansion contraction cycles, the buffers are good because they limit very much the interaction, and you don't get a buildup of pressures. But for the seismic case, the more you load the embankment, the least you load the foundations. So it's really a matter of sensitivity. I don't have that sensitivity to tell you. Now, case by case, you should decide what is the most economical design. As for the not having inelasticity in the foundation, you know, some like plastic hinging in the piles is admitted even in this is general. I said it in part one, in the webinar 2.1. It's not just a matter of integral abutment bridges. You can have plastic hinging when it's unavoidable. For instance, you may have plastic hinging in piles where you have a discontinuity in the soil layers, and you go from a softer layer to a harder layer. You may intentionally do that because you want head-bearing piles. No, in that case, you have kinematic interaction and impose. What you cannot do is to rely on that as a source of energy dissipation. I wanted to make this comment. It's not like there can't be plastic hinging in the piles.
Okay, thanks. So there are two short questions. So which kind of piles is more suitable, in integral bridge, in seismic regions, concrete or steel pipes?
I don't know. I can't answer. I don't have the.
It really depends on the local.
Yeah, unlike my colleague Telemachos Paranjotakos, I'm not a designer so I didn't see as many cases to give a proper answer. Let's say supported by you know, a statistical basis for this. So I wouldn't venture into saying which one is better. Of course, steel piles are more flexible. I think that it also depends on the solution you choose for the embankment and the interaction with the embankment. No?
Okay. Yeah.
It's not just the piles.
Okay, so there is another short question. Is the displacement method design of bridges going to replace the force-based in near future, especially in bridge types other than integral bridges?
In bridges, sorry?
Other than integral bridges. That's
okay. Nice. Thank you for the question. I think it's a very relevant, important question. I think that the first push towards is let's say phasing out of force-based design and moving to displacement-based design is in a Black workshop in 1997, the first workshop of performance-based design. We all know that the earthquake imposes displacements of structures, does not apply forces. And forces are just a result of the resistance we give to the structure. So displacement-based approach is, let's say, physically and conceptually the most suited one. Now, of course, civil engineers are used to forces and would like to keep using forces. I don't think we need to be philosophically more consistent for the sake of it. We should be practical. Probably most structures will keep being designed in force-based terms with added displacement checks for still some time. I think it's most, especially in low seismic action areas. I think this is especially true for buildings. For bridges, it will be probably much easier to switch to displacement-based design because these are structures that are, let's say, easier to model and for which carrying out, for instance, a response history analysis is most often the most sensible thing to do. And I know Italian practice, it is often the thing that is done. So when you do response history analysis, you don't do it with the Q factor. No, so it's inherently ready for displacement-based design. So there is a likelihood that if this transition starts, it will start more with bridges than with buildings.
Mm-hmm. Okay, thank you. So there is one question remaining, but I would kindly ask you to answer this question in the chat. There is another question because the time is running out. So at the end, I would like to express my gratitude to the organizers of today's meeting and to all speakers to take the time for preparation, for giving the lectures, and to present it in a clearly and understandable way. Furthermore, I would like to thank Rita Bento for the perfect organization and also the technical staff, and my colleague, Ms. Dietlinde Köber from the chair, to have the chair with me. And in conclusion, I would like to encourage you to use the webinars, which are freely available online and can be accessed anytime, whenever you have problems, and you will check the details so you can make use of these webinars. And that's also, let's say, a chance for the practitioner to get this information quickly and easy. And finally, I would like to thank you all participants for participation on behalf of the European Association. And yeah, I wish you a nice weekend. Indeed, over to Rita, which, yeah. Okay, so you have to close your presentation.
Yeah.